Sounds like it's on. It's on. Good afternoon. I'm Noel Schultz, and I'm the director of the Institute for Northwest Energy Futures. And we welcome you today to our second panel. We did a panel last year on small modular reactors, and so we're continuing that panel. So I just want to talk a little bit about INEF. So INEF is an institute that was funded by the legislature to look at energy as a system and not be in our silos. And so we're working with industry, with national labs, as well as the community to look at how do we get towards other solutions, resilient solutions for the future as we look at the energy space. When we first started talking about INEF, we looked across the WSU system and we thought there'd be 10 to 15 energy related entities. We found 25 related entities for energy. And so one of those is the food, energy, water nexus, which is very important, particularly in this region. We also have generation, the grid and loads. We hear a lot about that these days in the newspaper about generation and loads. Biofuels. Over in the Bessel building, we do a lot of work in the biofuel space. And we're also looking at systems perspectives, techno-economics. We're looking at the different funding sources. What is the cradle to grave of a technology and its costs to be made as well as producing energy? And policy. How do we look at policy to make sure we're making sure there are no roadblocks along the way? So the website's right here. We will have the video posted and the PowerPoint posted. So you can go and see that. And we welcome you to look at the INEF website and keep in touch with us. So with that, I'm going to turn it over to our moderator, who doesn't really need an introduction for probably most of you here. But Sean O'Brien is the executive director of the Energy Forward Alliance, or EFA, a clean energy nonprofit subsidiary of our local economic development organization, the Tri-City Development Council, known as TRIDEC. EFA is a community-formed organization helping drive clean energy innovation and partnerships in the Tri-Cities region and to build a reliable and sustainable clean energy future. And Chancellor Haynes was proud to help start EFA along with several other leaders of major institutions in the Tri-Cities area. Sean is a former executive director of the Congressional Western Caucus, a coalition of more than 100 members of Congress whose mission is to represent the voices of rural communities across the country and in our nation's capital. He previously served as a deputy chief of staff and legislative director for Congressman Dan Newhouse of Washington's 4th District, during which he was the lead staffer in handling the congressman's energy, public lands, Hanford site, and natural resources portfolios. He is a proud ZAG and as the immediate past chair of the Tri-Cities Legislative Council. Help me in welcoming Sean.
Good afternoon, everybody. Good to be with you. Let's see, Aaron, can you hear me online okay?
Yep, you're great. Thanks, Sean.
Since we're here to talk about critical minerals this afternoon, I figured I should start by acknowledging that the conversation really does get to the core of our energy future. Woo! And I promised to not take the discussion for granted. But if the puns do get too bad, feel free to minor your expectations. I didn't know that one actually. Sorry. All jokes aside, I thought it would be fun to kind of frame this conversation just real quickly. According to the International Energy Agency, a typical electric vehicle requires about 6 times more mineral inputs than a conventional car. The smartphone in your pocket contains more than 30 different minerals and elements. Things like cobalt for batteries, gallium for semiconductors, tantalum for the tiny capacitors that keep your device running smoothly. So Whether we're talking about those devices in our pockets or grid scale batteries, wind turbines, advanced nuclear reactors, the energy conversation today is more than just about the fuels now. It's really about those materials. And so that's what makes today's discussion so important for our region. You know, here in the Pacific Northwest, and especially right here in Tri-Cities, we're fortunate to have such an incredible ecosystem of expertise working on these issues. From research right here at WSU Tri-Cities to material science, energy innovation at PNL, to industry voices that are helping shape responsible mining and mineral supply chains across the West. Today's panel together brings leadership from across the ecosystem to better understand a few key questions. What exactly is a critical mineral? Where do these materials come from? How are they mined and processed? And how do they ultimately show up in the energy technologies shaping our future? So each of our panelists are going to have a short set of opening remarks to give a bit of an overview here, and then we'll open things up for discussion and Q&A. So I'm going to run through intros of our panelists real quick, and then we'll get to the meat of things. Erin Benson is an assistant professor of critical minerals at WSU's School of Environment, and she is an INEF faculty fellow. She studies the geologic processes that form ore deposits over millions of years and is particularly interested in rare earth elements. She was a research fellow with the U.S. Geological Survey prior to her appointment at WSU, and she received her PhD in earth science from Duke University. She was born and raised in Spokane as well. Go Zags.
Oh, bad.
Navajit Lahiri is a research scientist at PNL. He received his PhD in chemistry from the University of Utah, where he developed synthetic routes to conductive and redox active 2D metal organic frameworks. Mouthful. At PNL, his work broadly focuses on utilizing a suite of characterization techniques such as X-ray photoelectron spectroscopy. Man, I practiced that one. X-ray fluorescence spectromicroscopy and electron microscopy tools to understand crystallization mechanisms and the reactivity of minerals, as well as engineered nanoparticles for applications ranging from geologic carbon sequestration to corrosion science. Yes, Navajit, good to have you with us. Sid Smith is the government affairs manager for the American Exploration and Mining Association. He joined the association in 2019 after 17 years in the United States Senate. He began his career working for U.S. Senator Larry Craig in Washington, D.C., and spent more than a decade on the staff of U.S. Senator Jim Risch. Smith's time with the two Idaho members of the Senate Energy and Natural Resources Committee allowed him to build extensive expertise in a variety of public lands and natural resources issues throughout Idaho and the Pacific Northwest. And then joining us online, as some of you may have seen, it is dumping in the pass right now, which I think all of us are very grateful for the snowpack. But unfortunately, Aaron Fever wasn't able to join us getting over the pass, and more worrisome was trying to get home tonight. So we're glad he was able to join us virtually. Aaron is the WSU Executive Director for the Joint Center for Deployment and Research in Earth Abundant Materials. He has a background in the synthesis and processing of high-performance earth-abundant carbon and silicon materials. He co-founded two materials companies in the energy storage space, Group 14 and Energy 2. Fever and his team grew Energy 2 from a small venture-backed startup company to a 100-person manufacturing organization with locations in Washington and Oregon. Group 14, with operations in Woodinville, is focused on production of advanced silicon materials, which increase the energy capacity of lithium-ion batteries. He has spoken and written extensively on material science and engineering, as well as the specific use of carbon and silicon materials in transportation and clean energy storage applications. Could you please welcome all four of our panelists? Thank you. We're going to kick things off and turn it over to Erin Benson, and we'll head down the line from there.
Thanks, Sean. All right. So we can't really have a panel about critical minerals without first defining what a critical mineral is. So that's what I'll be talking to you about to start us off today. So as Sean has already covered a little bit, critical minerals pretty much fundamentally underlie a lot of our modern technology, right? Cell phone in your pocket, the energy that we are using to run this panel right now, the car that you drove to get here, particularly if you use an electric vehicle. All of these things and many, many more are powered or fundamentally generated from critical minerals. So when you think critical mineral, you think mined material, right? Something that comes from the earth. But beyond that, you may not have a great visualization for what that means. You may think of gold or silver or copper. Some of those are critical minerals, some of them are not. We define a critical mineral by two factors. So the first factor, as you can see on this bar chart on the left, is the impact that that mineral would have on our national economy or our national security if we lost all of our reserves of it. So if it fundamentally underlies something that we manufacture a lot of, something that we need for national defense, something that we need for energy, that is one part of the definition of a critical mineral. The other half is the risk that we run of losing our supply of that mineral. So if we have really, really good domestic reserves of a mineral and we have a lot of domestic processing capability and that supply chain isn't at risk, fundamentally, that's not really a critical mineral because we have such a good supply of it. If you have a supply chain with one point of failure, particularly if that one point of failure is based on our supply chain or trade relationship with another country, that material is much more likely to be a critical mineral. So a mineral has to have both of those characteristics in order to meet our fundamental definition for a critical mineral. That means the critical mineral list is going to be different for any country that you're talking about, right? Every country has a different trade relationship with other countries. Every country has different domestic geological endowments, like where you would go to mine a deposit. So our critical minerals list is going to be different from Russia's or China's or a South American country or European country or any other country in the world. Our list is updated every 3 years by the US Geological Survey. The most recent iteration actually came out in 2025, November of 2025, so very, very recently. It added 10 new minerals and took a few off. So we are now at a list of 60 different critical minerals. As a brief aside, I'm just going to say as a geologist, critical minerals is a very evocative term for what we're talking about, but it's not a very accurate term. A lot of the things on the list are actually elements, right? They're not minerals. We use the term critical minerals because it implies a resource that you're mining from the ground. But many geologists, if you tell them you're interested in critical minerals, will be like, do you mean critical elements? So just be aware of that. It is terminology that has a history. There's reasons that we use it, but many of the things on this list are elements. Some of them are actually minerals. Graphite is on the list. Phosphate is a group of minerals. Barite is a mineral, so that's barium, carbon, phosphorus, respectively on the list. But as you can see on the list, this list of critical minerals is a huge portion of our periodic table, right? That's a lot of different elements. My research specifically focuses on rare earth elements, so that's the example that I'm going to be using today. You may have heard in the news about rare earth minerals. So a rare earth element is actually a subset of the total list of critical minerals. So a critical mineral is anything that meets those characteristics that I described before. Rare earth elements specifically are actually a chemical classification for a specific grouping of elements. That's the lanthanide series that is in orange on the periodic table, plus scandium and yttrium, because they behave very similarly to rare earth elements. So when you hear rare earth mineral, that specifically means something that has those rare earth elements in them. Critical minerals, much broader than that. So when we're thinking about mining and critical minerals, we start with a rock. That rock probably has a pretty good percentage of whatever commodity you're interested in mining. But a lot of what's in that rock isn't what you're interested in. So you have to mine the rock that has a high grade and then break it down into its constituent parts. And that processing is part of our critical mineral supply chain. Sometimes that processing is actually where some of your supply chain bottleneck is if you don't have the domestic capabilities to process your own critical minerals. So for rare earth elements, China is actually our big supplier. Over 70% of global rare earth elements are produced in China, mined in China. The US has one actively producing mine, that's Mountain Pass, just south of Las Vegas. But a lot of our rare earth elements are still processed in China. Because they produce so much of it, they have the ability to break down those rare earth minerals into the constituent element parts. And so China controls a huge point in our supply chain. And that fundamentally is why pretty much all of the rare earth elements are on the critical minerals list. So when we think about geologic materials, these are materials that occur naturally at very low abundances in a lot of different rocks. When we think about an ore deposit, that is a place where geology has given us a very, very high concentration of those elements for one reason or another. And that's a lot of what I study, is why ore deposits end up where they are. But that means that when we're thinking about different mineral commodities, some countries will naturally have a lot more, some countries will naturally have a lot less. And that's where we start to get into those issues of mineral criticality and supply chains, right? So as you can see, a lot of our rare earth element deposits are geologically located outside of the US. We have some, but we don't have nearly as many as countries like China or Russia, or even Vietnam or Brazil. So that, in summary, is our general overview of critical minerals and some of the issues that can come along with them. And I will now turn it over to Sydney Smith, who's going to talk to you a little bit about mining byproducts and mining basics.
Great. Thank you for that that quick run through and that introduction, Aaron. That was good foundation for what I'm going to talk to. So a quick little background about our organization, American Exploration and Mining Association. We are an industry association. We were founded in 1895 and we are based in Spokane. Back then we had a different name, but we've always been headquartered in Spokane. Today we're a nationwide association. We have about 1,800 members in 46 states, and our members are focused on exploration and early phase development, those two sectors, and our members are in primarily the Western states. Mineral deposits, I think if you can take one thing away from what I say today, mineral deposits are rare geologic phenomena. Despite that map where they're kind of scattered all over the world, they really are hard to find. And unlike $1 million or $1 billion projects like a data center or a power plant, mines can only be built where they are discovered, where minerals are discovered. And so if we close off lands, if we decrease, then we end up decreasing the odds of making that next mineral discovery. And so in the West, with so much federal ownership, access to federal lands and permitting processes are really some of the biggest issues that our members worry about. And, as we communicate these priorities to our members, we really like to talk about the fact that if it isn't grown, it's mined. And that seems really basic, but it's something that ends up getting lost over time. But we have to return to that quite a bit. But, pretty much, we've mentioned this already, but pretty much everything that is in this room comes from a mine or in a processing plant. And from the moment you woke up today, your life has been influenced by mining. The subset that we're talking about, critical minerals, it's been gaining a lot of recognition over the last couple of years around the world. Something that I'm going to mention or point to here is what we call, this was in the USGS mineral commodity surveys over time, up until last year. It's called what we call it anyway in the industry, sometimes the wheel of minerals companionality. And what that illustrates is in the center there, you'll have minerals that are frequently pursued by exploration companies looking to develop a mine. You'll see gold there, copper, iron, titanium, and it shows other minerals that are frequently found with those elements in a deposit. Not always, but pretty often. And so with gold in the center there, if you move out, you'll frequently find minerals or elements like silver, copper, zinc, antimony. If you look at titanium, you'll quite often find rare earths there as well. This is important to understand because when you get your drill results as an exploration company, you're going to have to look at that entire buffet of minerals that come out in those cores. And so the economics really have to pencil out as you make that decision to go forward. Are we going to pursue this project or not? And as Aaron mentioned, Critical minerals, a lot of them, there's a whole list in the United States. There is actually differences between different agencies within the United States. USGS has one list. The Department of Energy has a list. DoD, Department of War, has their own list. And so gold is a very glaring omission in our opinion, because the production of gold in the United States and around the world enables the production of many other critical minerals, in fact. And if gold is not produced, a lot, as you can see from that wheel, a lot of other critical minerals will never come out of the ground that we use and we need very dearly. So this takes me a little bit further on, you know, as my panel colleagues will tell you, geologic processes take a lot of time and, you know, millions or even billions of years. And sometimes we in the mining industry feel like it takes that long to get a mine built. But the exploration phase, you know, it's not totally unjustified to feel that way. The exploration phase can often take 10 years or more. The National Academy of Science notes that there only 1 in 1,000 exploration targets will ever actually turn into an operating mine. AI can actually help narrow that down a little bit and speed it up, but you still actually need individuals' boots on the ground out there to speed that, or to verify what your model has spit out. The permitting phase takes even longer, unfortunately. In the United States, we are one of the slowest in the world, and there's good and bad things to that. But once you get to that decision to proceed through permitting, you have to conduct a number of things like baseline studies to determine what the status of the surface water, the groundwater is, soil, the presence of threatened or endangered species, or the absence. You have to do community outreach, tribal engagement, several rounds, most likely, of financing. We do calculation of financial assurance, also known as bonding. Reclamation and closure planning take place during the permitting process. And notice that we plan before we get our permits for financial assurance and closure. And that is to ensure that no new abandoned mines are created and taxpayers aren't left on the hook. If a company goes bankrupt or market conditions change. And that's a big change over the last 30 to 40 years within the industry, and it's a positive change. But you know, NEPA takes another big chunk out of that 20-year time frame. It's another good 3, 5, 8 years. NEPA, yes. Sorry, I'm starting to talk in jargon. The National Environmental Policy. Yeah, I almost said permitting, so I had to catch up. The National Environmental Policy Act. And that is a worthy process, but it can get things bogged down quite a bit, a procedural tool. Beyond that, the Clean Water Act, the Clean Air Act permits are required there, the National Historic Preservation Act, and a whole slew of others. Local and state governments have their say as well. Upwards of 60 permits are required for any given mining project. And so that is a lengthy process. And there's also legal challenges that play a factor there as well that can add 2 to 3, 5, maybe more years into that. So as a result, mining projects usually require billions of dollars of investment, and they face a great deal of regulatory uncertainty in the United States. One project that I have, we have from what I call the Heartbreak Hotel, is a member who spent $500 million over 10 years going through the permitting process. But once they were at that point, they actually had the Forest Service pull their permitting, their leases, and BLM initiated a withdrawal of the land. And so they're at that point where they're actually got a steep hill to climb. It's not completely a dead project, but it doesn't look great. It's going to be difficult for them to get to the finish line. Aaron mentioned the Chinese hegemony in the mineral markets, and that is a difficult thing that we're having to contend with. Chinese state-owned companies really do have a tough grip on the mining industry worldwide. That second project that I have on that list there, just in the central mountains of Idaho, the Idaho Cobalt project was about to go online. The price of cobalt was $40 a pound, which was near a record high. But as that project neared commissioning, cobalt mines that were controlled by the Chinese state companies began to ramp up production, flooding the market. And within the year, the price plummeted from $40 to $9.50 a pound. And that mine has never come online. And maybe a while if they ever do, frankly. So to kind of start to wrap up here, I'll say that in the last 5 years, the dangers of our dependence on foreign sources of minerals have become really impossible for us to ignore. With the COVID-19 pandemic, Russia's invasion of Ukraine, and now in the last 2 years, really, the Chinese government has either cut off or severely restricted minerals that are vital to national security applications through export controls or other means. You know, critical minerals are being viewed with a new sense of urgency here and around the world. Our mineral endowment here in this country it rivals almost anywhere in the world. But for many years, we've outsourced our mineral supply chains. We have awakened to the fact that the nations producing minerals where we supply our mineral supply chains come from, they're not always friendly, these countries. And the conditions in which the minerals are produced over there are often appalling, frankly, in terms of environmental standards and human rights. We can and we are turning this around by reviving our domestic mining industry, which is the safest and most responsible mining industry in the world. And that's something that we can be proud of. But that turnaround is going to take time, discipline, and a sustained focus. So I really appreciate your attention. I appreciate the opportunity to be here, and I look forward to taking questions and continuing the conversation. Thank you.
Sid, and good afternoon, all. I'm going to talk today, I'm going to follow up on what Sid was talking about and talk about non-traditional mining. And if there's one takeaway from this is that we need to go beyond conventional mining. In order to meet critical mineral demands, we need to adopt these non-conventional approaches. So before I talk about that, let me pivot a little bit into how critical minerals are currently mined. So this is a photograph of the Kennecott copper mine in Salt Lake City. It is big. You can actually see it from space. There are photos of it from space. This is an example of open pit mining, which is one of two primary critical mineral mining technologies. The other one being underground mining, where you have an extensive network of underground tunnels. In both of these cases, you're excavating large amounts of rock. And that has kind of been the standard for critical mineral mining for the past century or so. And what happens to this rock when you excavate it? You process it partly domestically, and then, like other panel members here talked about, this is then shipped over to China or some other country overseas, an adversarial country maybe. And that introduces a supply chain risk because most of the chemical processing is likely done at those overseas sites. And then you have to import the copper back from those countries from the same mine that was dug up. It's a large hole now. And just a quick fun fact, well, not really fun, it's a little dire fact, but an average US house to be built requires about 40 tons of ore from that mine to be displaced, which is a huge number. We don't really think about where things come from and how they're mined and where they're mined, but I think that is going to be a theme across this panel here. And the other point that Sid mentioned here was the permitting time. To be able to permit a mine like this takes anywhere between 15 to 20 years. A recent estimate has shown that in order to meet business as usual demands for copper, just business as usual, by 2050, you will need 36 of those come up. That is a near impossibility. And now that we realize this, now that urgency has really come to the forefront. How do we alleviate these? How do we mitigate these risks? And that brings me to non-traditional mining, which not only alleviates a lot of conventional mining risks, but is beneficial and lower cost in many instances. My work at PNNL is focused on one type of non-traditional mining, which is in situ mining. In situ mining, we're not moving rocks. We're not excavating rocks. The rocks stay where they are. We're moving fluids. So what we do is very similar to what the oil and gas industry has done for decades. We will inject a fluid that is a water-based fluid in the subsurface, and then that fluid will then leach out the critical minerals. The rock stays where it is, and we then extract that fluid back up using producer wells. And so we're not excavating rocks. You're not ending up with waste rock on the surface. Now, mind you, that copper mine I was showing you, only 0.5 to 1% of that contains the copper we need. So the rest 99 to 99.5 is just waste. And where does that go? That just sits around on the surface as waste and being an environmental issue. The other advantage of non-traditional mining efforts like this is that we can now target new resources. We can now target more unconventional resources. Because we're not moving rocks, we can now target lower grade resources. And that expands our critical mineral domestic reserve. And we're getting a fluid out of it at the end of the producer well. So that's the same thing that these adversarial countries, they're processing it to a fluid, and that's what we get out of the wellhead domestically. So we can process it to a metal on site or somewhere within the United States, alleviating a lot of that supply chain insecurity. And you can imagine that because we're not moving rock, there is much less surface disruption. And surface disruption is a key aspect that keeps permitting from, becoming a shorter timeline for permitting, right? Some of the other non-traditional mining approaches are things like bioleaching. Bioleaching is another emerging technology. Copper is one example where bioleaching is actually starting to ramp up in a commercial process. And then you have rare earth elements being mined using bioleaching, where basically you're using bacteria and the acids they generate to extract critical minerals from rocks. And then there are more emerging technologies that are non-traditional, like you have phytomining, where you have plants growing on top of rocks, but these plants are hyperaccumulators for certain types of minerals. So you grow these fast-growing plants, and they will accumulate critical minerals in their stems and leaves, and then you can extract it. And the same goes with algal mining. There's deep sea mining where you mine nodules, polymetallic nodules that are rich in elements like cobalt, manganese, nickel, all that go in battery materials that you can mine from the seafloor. So to wrap up here, what I'm trying to say is we need to be more open. We need to think about, we need to research, we need to deploy these non-traditional mining tools in the very, very, very near term, or else we're not going to be able to meet our critical mineral demands. And we are definitely going into a situation where we will end up with severe supply chain and energy insecurity within the US. And a lot of these technologies, they enable lower cost mining. A lot of these technologies enable faster permitting production. And like Sid was mentioning, a lot of these technologies also enable byproduct mining, where you're able to maximize the full value of the subsurface asset using these technologies. So I'm happy to be here. I'm happy to discuss more on this. Thank you.
So I'll invite the in the room audience to note the monitors on your sides. You'll be able to see our next panelist, Aaron, there. And then Aaron, don't hesitate to give me a shout when you're ready to move on to the next slide.
Okay, sounds good. Thanks a lot, Sean. And wow, thanks everyone. This is I don't think I've ever had a better introduction to the topic of critical minerals to date. So I really wish that I could be there with you all in person. Can't believe this very small amount of snow that has landed in the Cascades this year as compared to the amount that's landing in the next 48 hours. It's a little bit. But anyway, I'm glad I could join you online. Thanks again to David for pulling together the IT solution so quickly. So yeah, Sean, you could just go ahead and go to the next slide. I don't feel like I need to talk too much about what critical minerals are, what the issues are, and can just focus a little bit on what JC Dream is working on to draw attention to the solutions. So JC Dream was created in 2015. I originally joined on the board of directors as one of the company representatives on the board. It's a statewide organization with representatives from all the major educational institutions, PNNL, a bunch of industry representatives, and we focus on these issues across the state of Washington. The reference to earth abundant materials is of course the opposite to critical minerals, and it's kind of a tribute to the fact that we are trying to tackle some of these solutions. The specific mandate of JC Dream is to focus on the critical mineral challenges in the clean energy and transportation sectors specifically, and I think that's a really smart move on the part of the state of Washington. It was created by the Washington State Legislature back in 2015, and they recognized that we were undergoing a major transition in the energy sector and the way transportation technologies are going to be deployed. And when we think about the sheer volume of our current energy infrastructure, just in terms of the massive amount of fossil fuels that's extracted, all of the transmission architecture, all of the fossil fuel related energy generation structure, all of the transportation infrastructure, automobiles, diesel, airplanes, all of it, all of the maritime sector, it's massive, right? It's just a huge amount of material. Literally, just the tons of minerals and stuff that is deployed in order to make all of this technology work. And we are in the middle of transitioning that from the old fossil fuel related technologies to modified and new versions that are focused on different and clean energy options. And all of those technologies are heavily dependent on minerals as well. And so we are at a major transition point, and now is the time to really make sure that we focus on the critical mineral challenges that we have and the earth abundant alternatives and other sources of materials that we can go after. So at JC Dream, we've looked across all of these energy critical materials. These could be things like the battery critical materials like lithium or cobalt or graphite. You'll see in the hydrogen economy, there are things like platinum and iridium. The solar and semiconductor industry relies on things like gallium and germanium and indium. Of course, the rare earths are a major component in things like electric motors, where we're using magnets, or in wind turbines. We have nuclear materials like uranium. And so all of those areas are some of the specific focal points of JC Dream. The tough thing is this is deep, hardcore material science to go solve these challenges. So we started out trying to tackle some problems by addressing these challenges with seed grants, and had some really interesting research done at a number of different universities here in the state. We landed on the fact that Washington State has a number of interesting assets that make it a good place to deploy and focus on hydrogen. And so we saw an amazing nexus of expertise at WSU, PNNL, and some of the other institutes in the state doing amazing research. We recognized that we had a clean power grid in the state of Washington that was really second to none in terms of the ability to use that clean power to generate a clean, sustainable fuels, including things like sustainable aviation fuel, biofuels, and hydrogen itself. And then we also recognized that we had a lot of the transportation sector in the state of Washington is going to need something besides battery electric drive systems. So things like airplanes, heavy duty, long haul trucks, maritime applications, transit buses. These can, in some cases, use battery electric systems, but really hydrogen or sustainable fuels is the path that makes the most sense. So we created the Charge Innovation Cluster, which is an organization that you can see their logo down there. And we just created an H2MI initiative, the Hydrogen Mobility Initiative, to focus on things like heavy duty transport, hydrogen trucks and buses, and things of that sort. So we've been hard at work trying to bring critical mineral issues to the forefront of that rapidly evolving hydrogen economy. We also have recently, recognizing some of the workforce development challenges and the fact that a lot of folks are really not aware of these critical minerals, we've started on a curriculum development program for K through 12 students, actually. So that's that rare earths page down there in the middle lower part of the slide. We're developing a few different curriculum modules that are targeted towards middle school students, recognizing that, hey, we oftentimes lose kids that are not as interested in science or math, especially women and minorities in this country, that sort of veer away in different direction because they maybe don't understand some of these challenges and don't recognize that science is cool and there's a lot of really interesting challenges to solve. So we're working on that curriculum development. And then on the lower left-hand corner, you can see a couple copies of some of the reports that we've issued. We've done 4 of these now. The first 2 were focused on the critical mineral challenges, generally across all of Washington State. Another one focused on the hydrogen economy. And then just in the last few months, we released these that are focused specifically on the AI challenges. So AI, of course, is consuming massive amounts of power in our state and across the country, and that has a lot of critical mineral implications. And then in addition to that, just the sheer massive amount of computing power that's being deployed has a whole host of critical mineral issues related to semiconductors using advanced materials and advanced chips that incorporate large amounts of gallium and germanium and other things of that sort. So we're trying to draw some attention to those kinds of issues, again, recognizing that AI is another one of those sectors that's really relevant to our state, and also a massive deployment of resources that is growing extremely rapidly. So those are some of the things that we've focused on at JC Dream here over the last 10 years or so. And with that, I don't want to take too much more time and want to open it up for discussion. So back to you, Sean.
Everybody, please thank Aaron Fever for doing this. So we're going to open things up now to Q&A and discussion here. Want to make mention for our folks who are online. I think Noel included a mention that you could drop your questions in the Q&A or in the chat function there. We'll turn it open to folks in the room as well, but maybe just to kick the conversation going, we had asked folks who registered if they had any questions initially. And there were two topics that we received many questions on. The first is on the full life cycle and recycling and what kind of solutions are in that space. So I think I'll just open-ended for any of our panelists who'd like to jump in. Can you talk a little bit about the recycling side of the house here and what are some opportunities and perhaps also challenges in that space?
Well, yeah, I don't know. Yeah, am I coming on there? I think it might be. But anyway, I'll say, sometimes there's a perception that perhaps with the mining industry that we'd rather just see mine or recycling go away and just mine, baby, mine. But I think we are actually really rather friendly to recycling. The magnitude of our mineral demand, especially in the next 25, 30 years, is so massive that we're going to need all hands on deck. And so we're going to need to scale up recycling. We're going to need to scale up just about everything. But it is also important to understand that even if we massively scale up recycling, it's not going to come anywhere close to meeting the mineral development. So I've seen a number of reports, and these are not industry generated reports, but usually from the conservation community, that even if we actually, I think IEA, actually, the International Energy Agency, produced a report a few years ago that if we reached 100% attainment of recycling 100% of our minerals that are the metals that are out there, it would only need about 10% of our need. Some of the conservation community groups have estimated that we could hit higher amounts of our demand, but still nowhere near 100%. So I'll leave it there. I don't know if anybody else has anything to add in.
I'll chime in real quick. It's a fantastic question, and I'm really glad that was asked. It's something that is inherently, pretty challenging in some of these spaces. We're accustomed to, aluminum cans that can just be melted, and then also things like plastic recycling that everybody sort of thinks works, but it actually doesn't work, right? And so we've got to kind of thread the needle and figure out some of those things. The good thing we've got going for us is a lot of these materials are really quite valuable, and harder to come by than some of the more common things. And so consequently, we've seen things like, Apple has really been pretty successful in growing iPhone recycling, and a lot of the critical minerals that are present in consumer electronics are being recycled at a much, much higher rate than they were many years ago. So people are making progress. The electric vehicle space and battery technology is kind of my home territory. It's been a tough one, right? You see that the volume wasn't really there in the early days. And so it took, when you look at electric vehicle batteries, they have a 10-year lifetime or something like that. So you don't actually, in the early days of deployment, people don't think about recycling technology because they don't actually have that feedstock of used 10-year-old electric vehicles floating around. And so in, say 2012, 2014, when a lot of electric vehicles were first becoming popular, nobody was really looking into this. And they didn't really start to until around, just the last few years, when you started to get those first few, Nissan Leafs and Tesla Model S's and things like that reaching end of life. And you start to actually have enough of that feedstock material that you can go and work on that. But you're still starting from the beginning. You have to figure out a lot of them. What are the most efficient ways to do this? How do you dismantle those modules and get to separate the materials from each other? And all of these are a lot of challenges that we are right now in the throes of addressing and tackling those problems so that they can be scaled up efficiently and effectively. So I think this is an area where we're making progress, and it's definitely something that we've seen. Other countries do well with during the first rare earths embargo of 2010, when China shut off critical minerals supply to Japan, they really buckled down on recycling technologies and made a ton of headway. And so, I think it's some of those kinds of things that are sometimes the impetus for getting that going. But I think it's definitely an important focus area.
I would add also some materials we don't, well, as Aaron was just saying, we don't have really good technology to recycle yet, right? So rare earths, a very, very small fraction of what we have are currently recycled, partially because it's very expensive and partially because we just don't, it's more efficient to mine them, right? So it becomes a cost issue as well for some technology.
Yeah, I just like to add, I mean, these were all great points. Just adding on top of that is, I think the community in general can do a lot to make a difference. Recycling is one aspect of that that is accessible to the community, that they can make a difference in the critical mineral supply chain. The smartphone is a mine. Your any batteries you have is a mine. We in the US do not have any cobalt mines, but we all have batteries that have cobalt. So let's make sure we recycle, we recycle more. Many of these e-waste materials that we have, well, that might become e-waste have more percentage of metals in them than are present in the ore. So it is very critical for us to, as a community, make an effort to prolong the life cycle of the devices that we own, and also try and recycle more.
Great, thank you. If you have a question in the room, feel free to flag a microphone down your way. The second topic that we found in many of our submitted questions had to do with, given we are on WSU's campus, careers in this space. Can a few of you touch upon some of the career opportunities? Many of the students who submitted these questions were really focused about their interest in, the clean energy future and opportunities in the mineral space specifically.
Now I just did the opposite of what I meant to do, is mute myself. We'll take all of them. And not just the kids in mining focused programs. So obviously we are experiencing a real shortage of kids in those mining focused programs. We have more than half of the mining workforce that is eligible to retire by 2029. So we are in a crunch. Mining engineers, of course, and geologists and metallurgists and all those things that you would think of who might work at a mine site or a mill or a smelter or those sorts of things. But we also really need people who wouldn't think of themselves as miners or interested in mining. If you think of yourself as an environmentalist and wanting to protect the environment, we need you too, because we need people who are focused on helping us comply with our water quality permits. We have a lot of people who entered the mining industry from the conservation community and actually help us look at our mine plans critically and say, couldn't you make it a little bit, your mine plan a little differently and protect this resource over here? Make it a little smaller, make it a little different, that sort of thing. And those kind of critical eyes, a fresh set of eyes on some things are really very helpful. And so we need those environmental specialists, accountants, and you would be amazed at how many ladies are out there driving haul trucks, and we love it. If you don't think of yourself as someone who would be interested in mining, there is still a spot for you, and we'd love to talk to you. So,
Many excellent female geologists on the mine sites that I've worked at before.
And that is awesome news to hear too, Aaron. I was so glad when we recruited Aaron to join WSU, because when I first started with WSU, not that long ago, but 6 or 7 years ago, we had one outgoing geologist on that was one of our faculty members, and he left about a year after I joined. And there's most of geology's been in the environmental science space, which, no offense to environmental scientists, but I think we were kind of missing some of the hardcore, mineral geologists. So I think that's definitely an interesting area. There are, of course, I'm a material scientist, and so I feel like, material science and engineering is one of the core ways that we're going to tackle finding substitutes, finding ways to use critical minerals much more efficiently, finding ways to recycle them. That's definitely an area. I've worked with a ton of really fantastic chemical engineers in all ways, or all parts of the manufacturing and chemicals, mineral industry. This all relies heavily on lots of chemical engineering fields, and so there is a ton of opportunities. I just wanted to flag the Department of Energy actually just did a great career map that I posted in the chat that has a whole bunch of different kind of starting entry-level jobs that grow into various different directions within the critical minerals space. And so that's a really nice tool just to kind of give people a general sense of what's out there. But I did also just want to like flag the fact that I think our audience here contains a whole bunch of educators. And to the extent that any of you out there that are teaching, in higher ed or in K through 12, wherever that may be, figure out a way to bring this topic up. It touches everything. It touches every technology, out there. So it doesn't take, too much background homework to find the critical mineral issue that's, adjacent to whatever topic you're teaching, and definitely something that's worth a look for educators.
Thanks, Aaron. I think let's go ahead and jump to audience question.
Thank you. And thank you all for being here. Sid, I was particularly struck by your example of the Idaho Cobalt project, and especially the role that the Chinese Communist Party played in that. So as we move forward, it's really concerning the power that some of our foreign adversaries have in this particular space, not just on their ability to manipulate the market, but particularly also steal some of the technology that we may spend millions or billions of dollars developing to harness these materials. So can you speak at all to some of the things that we should be aware of or on the lookout for, or that we could do in the future to prevent another Idaho Cobalt project from happening? Or make sure it does happen.
That is a great question. I think one of the major issues that sank that project is that the runway was 15 years long. So it was really easy to see it coming and prepare from an adversarial standpoint. If you see it coming 15 years away, it's easy to kind of figure out some tools that you can use to tank it. So that is one of our initiatives that we're trying to take, which is to make our permitting process here in the United States not cutting corners, but to make it more reasonable and still very transparent. The S&P Global did a study just a couple years ago and found that of the major mining nations in the world, the United States takes the second longest to get a mine through the discovery and permitting process, of about 29 years. The only country in the world that was worse is Zambia. Out of the countries included in that study, I'm sure there are countries that are worse, but 29 years is way too long. I think we can demand from our policymakers that we do something about that length of time that it takes to get through that process. There There's a little bit of a movement, I think, growing that is focused on yes in my backyard. And of course, mines aren't going to be directly in your backyard, but we can support projects. Because up until now, there has been really an anti-mining sentiment in this country. But as people are growing more aware of where their minerals come from, I think it has followed the movement of like fair trade coffee. People have, really demanded to know where things are coming from. And, we call it like there's a Walmart beef syndrome for, people really up until the last few years have really lost track of where things come from, and things come from the store. And that's about the extent of where they think about it. But demanding to know the provenance of your coffee, your food, and now your minerals, I think is a helpful step. People are demanding to know from Apple, from other consumer electronics companies, where are these inputs coming from? And we do it better here. We're more transparent here in the United States. We protect our workers, we protect the environment. Those are a couple of things I think we can do to demand that projects are done here, to demand that they're done quicker. And I think our allies and the United States are working together to try and break that stranglehold that the Chinese Communist Party has on the mineral markets as well. That's probably another session we could spend a couple hours discussing, but that's kind of a quick overview. It's a great question.
One of the interesting facets of that specific project in Idaho was the incredible collaboration between not only industry and the local community, but also local environmental organizations were supportive of that cobalt project. And so the fact that it did die is really, really disappointing. No, I think we're going to go to some questions from online.
Yeah, I have a couple. The first question is, how much by mass fraction of the non-critical products are extracted from the soil per unit quantity of targeted critical minerals?
I can start.
Yeah, can you help?
Yeah, that's a very important thing to think about. Like I was mentioning in the slides, copper as an example, from that particular mine, we only get about 0.5%. I think in some cases about 1%, 1 weight percent, and then the rest is just waste. But then that brings us to the point that Sid was mentioning earlier, which is byproduct mining, because the waste that we generate is not really waste. It contains other elements, including non-critical elements, but also other critical elements present in there that we're not targeting because we're targeting the copper. But to answer the question, it's roughly around that range. It's about 1 to 5% in some cases, but not more than that.
It really depends on the deposit as well. Some deposits and some systems will have higher grade ore. So I know Mountain Pass, which is my rare earth element site, they get up to as high as 15% grade. They mix for, I think, about 7.5. But you're still discarding a huge amount of rock in that case. You can also talk about mining tailings piles as well. Sometimes a new material becomes critical that wasn't at the time that a particular mine was originally mined. And now you've got a pile of tailings on the ground that actually has something in it that we're very interested in. You can go in and reprocess those tailings for the new material that you've now realized is actually useful. And so that can be another way to use that already mined rock as well.
I always like to give people a little bit of a sense of the volume in very practical terms. And so now, Jeet, did you say that for an average U.S. American house, the copper would require about 40 tons worth of ore out of our Utah mine?
One of the 20 operational mines.
Yeah. So So 40 tons, I've done a little bit of my own landscaping. I have a concept of what 40 tons of rock looks like. It's a pretty close to the size of my house itself. Maybe a little less than that, like half the size of the house. And the copper in the house is just these little tiny wires, going to each outlet and each light switch and stuff like that. So it's a crazy amount of excess material that's discarded, right?
The reality there is that the easy ore around the world has mostly already been mined. The stuff sticking out of the ground that, 120, 150 years ago, that was easy for a prospector. There's gold, there's a silver, there's ore right there that I can see, and therefore I can, start something right here. Those high grade, easy to find deposits mostly have been mined. Now, the harder stuff that is lower grade or deeper down in the ground, that's what we're going after now. The good thing is that, technology has continued to evolve to make our recovery processes better, as Nabajit was talking about, but also even the conventional processes that we have. That's why, in the industry, and Aaron and I were talking earlier, we like to say the best place to look for a new mine is in the shadow of an old mine. A lot of mines are closed or abandoned, unfortunately, because back in the day, maybe 50 years or 100 years ago, they didn't have the technology to keep going, or the ore grade was not good, or they ran out of money. And so now we're going back into a lot of those and pursuing those with better technology and actually buttoning them up with modern closure practices, which is actually quite a good thing.
Yeah, I've got one more question along that line, and then we'll go back to the audience here. What key technologies are needed now to solve the current critical minerals problem in the US?
I'll start. My answer isn't necessarily going to be a technology so much as in order to find new deposits of rock, we have to understand how the ones that we already know about formed. For a lot of these systems, we still don't have incredible models for how they formed. So the tectonic setting, like where you would go to look for more of them, isn't super well constrained. That's what a lot of my research focuses on. If we know how the really high grade deposits formed, then maybe we can go find more of them that aren't sticking out at the surface, like Sid has said. So I'm not sure that that's a technology so much as just expanding our knowledge of where to look. But that to me is an immediate answer.
Yeah, just want to add on to that is that, new technologies that can target new resources, right? This has been iterated by the panel earlier is high grade ores are depleting and they're depleting fast. And so conventional mining technologies will not be profitable. So you're going to have to look at newer technologies that can unlock those critical minerals in a profitable way, but keeping in mind environmental impacts, that you can now unlock these vast resources that we have that were previously unminable.
I'm going to build off a little bit off of what both of you have said, because maybe a decade or so ago, Tim Cook from Apple gave an interview, and in the wake of this interview, he was highly criticized because he was asked about why companies relocate their manufacturing processes to China. And the question was really, is it about cheap labor? Is it about cheap materials and that sort of thing? And he said, no, the reason is because when you do that, when you relocate, what you're actually tapping into is a knowledge ecosystem. And so you have thousands and thousands of engineers that you can, if you have a problem, you have not just a few dozen who are specialized in this area, you have hundreds or thousands who are knowledgeable in this area. And so that's, what he was talking about, like, picking up a facility and leaving or relocating it. But this is also what makes me very happy to be here today. because you are all helping to turn that around in the United States. Washington State is helping to do that. You are all helping to do this and rebuild, because frankly, we are way behind in the race. The Chinese system, the Chinese government, they have several hundred universities that are producing thousands of mining engineers every year. And the United States, in just the 1980s, we had more than 25 actually mining schools here in the United States. And between then and today, we actually bottomed out at about 12. We now have about 14 because 2 have restarted. But we are only producing about between 160 or 200 mining engineers every year. And so we're starting to turn that around, but you're all playing a role in that today too, in showing some interest and encouraging people to get involved. And so rebuilding that knowledge ecosystem so that when mines need to be built, when processes need to be, or processing smelters and those sorts of things need to be built, when companies need to tap into a knowledge ecosystem and get kids interested, when they need someone to rebuild or design a circuit so that they can recover tellurium out of their copper smelter that they weren't recovering before, they have a lot of people who know how to do that. So I'm excited about just being here today and being part of that genesis.
Thanks, Sid. Did we have,
If I could just,
go ahead, Aaron.
I was just going to interject the kind of the Earth Abundant Solutions approach to solving this challenge, because you guys did a fantastic job of addressing the resource challenge. But I think one of the things that we do best in this country is engineering brand new, groundbreaking science and materials development and new technologies, right? And we've done this, in a bunch of examples that I can think of in the critical minerals space. Even here at Washington State University, we've got researchers that have looked at creating a hydrogen electrolyzer that has no iridium in it and works just as effectively on a nickel and iron catalyst, right? And so that's some work that was done in Pullman by Professor Yohei Lin. Or we have an issue with China controlling the almost entirely the whole of graphite supply for lithium ion batteries. So the negative electrode in a lithium ion battery is made of graphite. China mines 90% of it and refines 95% of it. I'm proud that my company, Group 14, has come up with an alternate silicon and carbon, a couple earth abundant materials that can be manufactured domestically or anywhere else in the world, and we're replacing that graphite supply. Same thing in the cobalt side of the lithium ion battery. You see, cobalt has been something that engineers have leaned on for high performance in lithium ion batteries for decades. But things like lithium iron phosphate, which is using iron and phosphorus instead of cobalt, nickel, and manganese in the cathode, are areas where we've developed cobalt-free batteries. These are all things that we developed here in the United States. China is fantastic at copying them and scaling them up and running away, but we invent these materials better than anybody else here in this country, and we got to do more of that. And so that's a big part of what I would encourage us to do is lean in on that groundbreaking material science, but focus on more earth abundant alternatives whenever we can.
Thanks, Aaron. Do we have a rapid fire question in the room?
Nuclear waste. Get your mic. Just a nuclear waste here that's. The nuclear waste that's right up here above us, and it's just an example of we attack the energy problem without having a solution. And you're talking a 20 to 30-year horizon, and a lot of this, it's scared the shit out of me. Because I'm here and allies in the US versus the communists, and it sounds like this raises the tension we need to look a little bit longer. We need to look a little bit longer so that we.
Did you
temper-
have a question, right?
Question is, nuclear waste up here at Hanford, and what did we think when we were doing it? And how are we gonna solve that kind of problem now? And mostly if we can recycle.
Maybe back on the recycling opportunities there.
Well, I think, I don't know exactly, I'm aware of the nuclear waste and the challenges.
And sorry, Sid, when I said
From-
there, I meant metaphorically, not there as in down the road at Hanford,
Right.
to be clear.
Yeah. So where I would go is that I think there is a lot of focus actually on waste streams right now in mining industry. Because as we kind of touched on it a little bit earlier, where old technologies were not always that efficient. And so there are a lot of places around the country, and actually a lot around the world, where waste piles have a lot of recoverable minerals in them, because the old technologies were only recovering, say, 50 or 60 or 70% of the mineral that they were targeting. And so there's a lot of interest in going back to those old waste piles, reprocessing those. And so as you do that, we're using newer technologies. And so when you do that, the waste pile that's there is smaller when it's done. And we put it into a new tailings facility or a new waste facility that is lined, so that it is not leaching anything into, say, the groundwater or surface water when it rains or that sort of thing. So those sorts of things actually they solve a minerals supply chain problem. They also solve an environmental problem by taking those old waste streams off the landscape. So those are some encouraging things that we're aware of. Perhaps you can chime in a little bit more if you have some knowledge.
Yeah, that's waste valorization. That's something that's critical. And then along with that, we need more technologies that can minimize waste just to begin with, right? Like you said, we don't want to solve one problem to create another. So we want to develop technologies that will generate less waste than conventional technologies, right? So that should be one of the focuses going forward, is how do we minimize that effectively?
Probably one thing I should add too is that, up until about the 70s or 80s, we weren't really, as an industry, required to plan for closure and reclamation. And now we do that as part of our mine plan. And so before we even get any of our permits, I mentioned it a little bit, but before we get permitted, we have to have a plan for closure and reclamation in place. And so when the mine ultimately runs out of ore and we have to close, we have to start grading slopes back to a relatively natural grade, and cap it with soil, natural soil, put plants back on it. And even the waste streams, they have to be accounted for so that they're not leaching chemicals and those sorts of things back into the environment in a much better, more responsible way than we ever used to before. So I think I'm hopeful that gets to what you're asking, not creating a new problem much worse than we started with.
So after the program, we're going to have refreshments in the back, and you're welcome to stick around and ask our panelists additional questions. As we shift toward wrapping up here, let's just do a very quick rapid fire. 15 seconds on what most concerns you about our challenges, and 15 seconds about what you're most excited about, what's most promising. And we're just going to go down the line. We'll end up with Aaron.
Start up with me?
Yep.
All right. So in terms of challenges, the timeline that it takes to bring new deposits online is very concerning, right? Even if we discovered all of the deposits that we need for 30 years from now, that's a lot to bring back online. In terms of opportunities that I see. Processing of waste, new processing technologies that can open up new supplies that we didn't previously have, I think is a real opportunity right now.
I think, yeah, we got a lot of challenges. We've got supply chains that are threatened. We've talked a lot about China, so I probably won't go into that again, but some of our windows are very short to break our dependence there. And we really have a talent crunch. We have to ramp that up really quickly. Our timeframes to build new mines are very, very short. They're too long, and we have a short time in which we need to do it. But we, like I mentioned, have a really formidable endowment of minerals in this country. So there's a lot of reasons to be optimistic. So 15 seconds, like I said, I could talk for hours about this stuff.
I think one of the biggest challenges we have, and this has been talked about in this panel, is the supply bottleneck, the supply chain bottleneck for mineral processing, and a lot of the mineral processing is now happening outside. Even though the mineral is from the United States, right? So a lot of new research needs to go into that, I think, to alleviate that in the very near term. New technologies need to come up that can circumvent those issues, and that's we do have a lot to be optimistic for, but there's a lot to do before we get there.
Go ahead, Aaron.
Yeah, I think probably China is the thing that I worry about the most. I think they are, we've already talked about some of their, devious activities in the mining and resources space, but they're continuing to, deploy and go after mines all over the world. They're starting to export a lot of the environmental and human impacts outside of China now. We're seeing things going on in Africa and Burma and things like that. So they're getting smarter about that, but still causing the same problems in other parts of the world. And they will steal intellectual property and all kinds of stuff without even thinking twice about it too. So it's a big challenge. But on the flip side, I'm very optimistic about our ability to innovate and come up with new solutions here in this country, as long as we get some of those workforce challenges solved and really bring all the resources and all the intellectual capacity that we have out there in all the young people that are getting ready to join the workforce. So that's why I'm
Thanks.
optimistic.
Thanks, Aaron. And just a quick plug from Navajit, if you want to go ahead.
Yeah, just a quick highlight. We will be P&L will be hosting a Critical Minerals and Material Science Summit. This will be 12th of May through the 14th of May. And we would really hope to have and love to have significant student participation in this. Shukta is here to answer any questions on that. Yeah.
Wonderful. Well, thank you to the WSU INEF team for putting this program together. Again, there are refreshments in the back for everyone. And if everybody could join me in thanking our panelists today. Thanks for coming.
Thanks, everyone. Once again, sorry I couldn't be there. Enjoy the refreshments.
Thanks, Aaron. Can we have the back? Yeah, absolutely.
Yeah, so I can take
All right.